In this part of our television measurement series, I'm going to be discussing differential gain. Diff gain is classified as a nonlinear distortion, which simply means that the distortion is amplitude dependent. Diff gain is one of several distortions that have to do with the interactions between the chrominance and luminance portions of the signal. Recall that a color television signal is made up of voltage levels that represent luminance or color brightness, and a high-frequency chrominance signal that contains the color information. Luminance and chrominance are added together to form the composite signal. Differential gain distortion is present when the amplitude of the high-frequency chrominance information has an unwarranted dependence on the luminance level that it's superimposed upon. If chrominance gain is affected by luminance level, there's differential gain in your system. The reason we're concerned about distortions like diff gain is that picture quality will be affected whenever some aspect of the signal isn't accurately transferred through your system. In the case of diff gain, it's color saturation that will be affected when the distortion is present. Saturation refers to the vividness of the color, the extent to which the color is diluted by white light. For example, red is more saturated than pink, even though they have the same hue. In signal terms, saturation is related to the ratio between chrominance amplitude and luminance amplitude. When luminance levels are correctly transferred, but chrominance amplitude is not, this ratio, and therefore color saturation, will be affected. Probably the most likely thing you'll spot in the presence of diff gain is that bright, highly saturated colors will appear washed out. It's usually most noticeable in reds and yellows. To measure diff gain, you need a test signal that places uniform amplitude chrominance at a number of different luminance levels. There are several different test signals which serve this purpose. This, for example, is a modulated staircase. As you can see, it consists of chrominance packets, all of which have the same amplitude superimposed on different luminance levels. This is a 5-step staircase, but some generators also offer 10-step signals. Another signal that can be used for this measurement is the modulated ramp, which you see here. Again, the chrominance amplitude remains constant while the luminance level changes. The basic principle behind making differential gain measurements with these signals is quite straightforward. Since all of the chrominance packets are the same size at the input, you can tell how much differential gain there is in your system by observing those same packets at the output. If they're no longer the same size, the system has distorted your signal. Here's a waveform display of a signal that is suffering from differential gain distortion. At first glance, it might look fine, but let's turn on the waveform monitor's chrominance filter to remove the luminance components of the signal. Now it's obvious that there's a problem here. Notice that the chrominance packets at the end, which should be the same amplitude as all the others, are much smaller. This indicates the presence of differential gain. Let's think for a moment about what can cause these kinds of problems in a signal. In a general sense, differential gain distortion is a result of the system's inability to uniformly process the high-frequency chrominance signals at all luminance levels. More specifically, the chrominance might be clipped or crushed as an amplifier is driven outside its linear range. As with most distortions, we want to be able to quantify the amount of differential gain so that we can communicate about it, monitor it over time, compare the performance of various systems, and so on. Regardless of the measurement method you're using, the amount of differential gain distortion is expressed in percent. The largest amplitude deviation between any two packets, expressed as a percentage of the largest, is quoted as the amount of diff gain. Strictly speaking, differential gain should be measured at different values of average picture level, or APL, and the worst error should be quoted. If the amount of differential gain distortion changes with APL, that is, after all, a level-dependent effect. This is obviously not practical for in-service tests where you're measuring a signal in the vertical interval, but keep it in mind if you plan to do a complete characterization of a system. Differential gain distortions can be measured in a number of different ways. We'll start by looking at the waveform monitor method, which relates most directly to our cursory look at the distortion. Here's the distorted signal again. While you could measure each packet directly from this display, it's easier if you enable the chrominance filter on your waveform monitor. This filter removes the luminance information from the display, making it easier to directly compare the chrominance amplitudes. One way to measure the packets is to compare them to the waveform monitor graticule. Start your measurement procedure by normalizing the peak-to-peak amplitude of the largest chrominance packet to 100 IRE. Then measure the peak-to-peak amplitude of the smallest packet. The amplitude difference, expressed in percent of the largest packet, is the amount of differential gain. If your waveform monitor has voltage cursors that can provide results in percent, the cursors can make this measurement easier. Let's go through the procedure with the 1780R. First of all, enable the voltage cursors and put them in the relative mode. Position the cursors to measure the peak-to-peak amplitude of the largest packet, and then press the reference set button to define that amplitude as 100%. Now move the cursors to measure the peak-to-peak amplitude of the smallest packet. The readout says 88.3%. The amount of differential gain is the amplitude difference between the two packets. So in this case, we have 11.7% differential gain, or 100 minus 88.3. This measurement can be made with almost any waveform monitor, and while it doesn't have particularly high resolution, it can let you quantify large distortions. Differential gain can also be measured with a vector scope. Remember that we're comparing chrominance amplitudes for this measurement, and chrominance amplitude is one of the kinds of information that we get from a vector scope. The length of each signal vector is directly related to chrominance amplitude. First of all, let's look at an undistorted modulated staircase signal on the vector scope. Set the phase to the reference 9 o'clock position and use the vector scope variable gain to bring the vector out to the graticule circle. We see one single dot because each chrominance packet has the same amplitude and phase. If we now introduce the distortion, you can see that several vector dots are now visible. Since the dots are spread out along the horizontal axis of the vector scope, we know that several different chrominance amplitudes are now being demodulated. This signal suffers from differential gain distortion. You'll also notice that the dots are spread out in the vertical direction when we distort the signal. This means that the chrominance packets also have different phases now, which indicates the presence of differential phase, another nonlinear distortion. It's common to see both of these distortions appear together. Remember, diff gain spreads the dots out in the horizontal direction on a vector scope, and diff phase spreads them out vertically. Most vector scopes have special marks on the left-hand side of the graticule to help you quantify these distortions. 5% increments for diff gain are shown horizontally. So we can verify that this signal has something more than 10% differential gain. This method, like the waveform monitor method, doesn't have particularly high resolution, but it does let you measure large distortions with standard test equipment. If, however, you need to measure small distortions or get highly accurate readings, you need an instrument which is equipped with a special display mode for making differential gain measurements. This capability is provided in 520A vector scopes or in the 1780R, which I'm using for this demonstration. This diff gain display shows you a line rate, voltage versus time sweep of the chrominance information demodulated along the B-Y axis. This signal is roughly equivalent to the signal that drives the horizontal axis of a vector scope. To select the diff gain mode, first enter the Measure menu and select Diff Gain. When you see the B-Y signal as a line rate sweep rather than plotted on a vector scope, the chrominance gain errors that stretch the vector dot out show up instead as level changes across the line. This type of display provides greater resolution and lets you see how the distortion varies over a line. The single-double selection in the Diff Gain menu gives you two slightly different methods of measuring this distortion. We'll first review the single method, which is what we're looking at on the screen now. Remember that we want to measure the maximum level change across the line. Since we want that level measurement to correlate directly with chrominance gain changes, it's critical that the instrument's gain be properly normalized before making the measurement. First of all, adjust the vectorscope variable gain control so the signal vector extends just to the vectorscope graticule circle. In addition, make sure the instrument's waveform monitor gain is in the calibrated 1 volt full scale setting. Now the instrument is properly set up for a single trace measurement. To obtain a reading in this mode, you need to compare the waveform to the vertical scale on the graticule and measure the largest deviation between any two parts of the signal. One major graticule division, or 10 IRE, is equal to 1% in this mode. With this signal, we can count up about 11.5 major divisions. So this signal has a differential gain distortion of 11.5%. Now let's make a measurement in the double mode, which gives you the capability of much more accurately measuring the amount of level change in the B-Y display. Instead of comparing the waveform to the graticule, you use a precision gain control inside the instrument to obtain a reading. Here's what the display looks like. You see the B-Y trace that was seen in the single display, plus that same trace inverted. Small calibrated gain changes move the inverted and non-inverted traces together vertically with respect to each other. The readout on the screen tells you exactly how much gain has been introduced in tenths of 1%. The measurement technique involves nulling out one extreme of the level difference by overlaying the two traces at that point. The amount of gain that needs to be introduced to null out the other extreme is then the amount of differential gain distortion. To make a measurement in this mode, you need to do the same initial setup that you did in the single mode. The vectorscope variable gain must be adjusted so the signal vector just reaches the vectorscope graticule circle. The waveform monitor gain is not critical in this mode, but we'll start with it in the calibrated position. The first step in the measurement procedure is to use the large front panel knob to overlay the largest negative excursions in the waveform. Now press the reference set button to set the readout to 0.0%. Then use the large knob to overlay the largest positive excursions. At this point, the readout indicates that this signal has 12% differential gain distortion. Remember that the buttons underneath the knob can be used to single step whichever function the knob is controlling. It's generally easiest to null out the trace if you use these buttons. As I mentioned, the waveform monitor gain can be changed in the double mode without affecting the calibration of the diff gain measurement. You can get even more resolution by increasing the waveform gain, as you can see here. There is an additional capability in this instrument that you might find useful if you're making measurements on noisy off-air or VTR signals. With noisy signals, it can be hard to resolve the displays and position the traces accurately. If you select Noise Reduction On in the Diff Gain menu, this enables a digital recursive filter inside the instrument, which will remove 10 or 15 dB of white noise from the display. Here's a quick recap of the nonlinear distortion called differential gain. This distortion is present when chrominance gain is affected by luminance level. It's measured by starting with a signal that has uniform amplitude chrominance superimposed on different luminance levels. Modulated ramp and modulated staircase signals are typically used. After this signal has been passed through the system under test, the chrominance amplitudes are compared and differences indicate the presence of differential gain. This measurement can be made with a waveform monitor with the chrominance filter enabled, with a vectorscope, or most accurately, with an instrument that has a special differential gain measurement mode.